Swayam Prabha. Digital India. Educated India.
But let me just quickly sort of talk about a few logistics. If you can, actually, that'd be great if you can turn your video on. If it's possible for me, if it's not possible, that's okay. It gives me a sense of talking to real people, which otherwise is kind of lost in this online meeting. So if you can turn on the video for however long you can, I would very much appreciate that. I have approximately 3 to 4 hours with you guys today, and I'm going to talk about a whole bunch of things, but it's not my intention to cover everything that I have on the slides. I have approximately 80 odd slides, but I don't have to cover everything. What I would rather have you do is, if you sort of feel like asking questions, feel free to interrupt me at any given point in time. I will try to take as many questions as I can, and if I see sort of the conversation drifting away, maybe I'll ask you to put your questions on hold and then take the rest of the questions towards the end of a session. Right. So I also don't like I don't like talking at you guys. I like these sessions to be as interactive as they potentially can be. So if I feel like there is not enough interaction happening, I just might cold call on you with questions. It's completely fine to say you don't know. It's completely fine to sort of attempt an answer and not get it right. That's completely okay. But I would expect you, if I cold call on you, I would expect you to sort of just try and participate. Right? Any questions on this so far? So I'll give you all 30 seconds or so to turn on a video, whoever can do that. Otherwise, you okay. All right. So what we'll talk about today is essentially the architecture of storage systems. I'll talk a little bit about hard disk drives as well as solid state devices, what they are, how they work. When we are armed with the knowledge of architectures of both hard disk drives and solid state devices, we'll move on to sort of the software stack side of things, where we see what file systems are and what are the file system design considerations and some of the optimizations that have been implemented over time in various kinds of not just file systems but computer systems in general to sort of optimize them mostly for performance. I think you guys might have sort of had sessions on architecture, maybe a review of the operating system as well, where you must have been sort of told a little bit about how operating systems behave, what or how a typical computing system on the CPUs behaves. And what I'll try to sort of do is tie what you have essentially been talked about to storage systems, which probably might not have been talked about this much. And the last session of the day, I'll sort of try and cover a bit of things that are state of the art in terms of storage systems research, both on the software and the hardware side of things. And then I'll hopefully be able to give you a sense of what are the research areas where some interesting work can potentially still be done. Right, so that's how the day is kind of divided into. I really don't have a lab or a demonstration session planned for today. So in the afternoon, maybe if you have questions, I'd be happy to sort of have a discussion around any questions or any one of the things that we might talk about today. If there are not that many questions and you guys still want me to talk about things that you might not be able to cover in, let's say, the 3 hours that you already have, I'd be happy to do that. Right? So that's briefly sort of the agenda for today. All right. Any questions on this so far? No. All right. By the way, I only see your first names, which are at the end of SS underscore. I'm guessing SS is summer school. So I'll just call you guys by whatever names I see after SS underscore. hopefully that should be right. So even before we get started, let's talk quickly about why we are here, why storage systems kind of or where storage systems kind of fit in the overall architecture of systems. And before we even get there, it's important to understand where we're coming from. Right? So where we're coming from is essentially from, let's say, a general purpose compute device, which for the most part, even if we set aside accelerators and all of those fancy things today, the general purpose compute is typically what is known as the von Neumann architecture. I mean, it's a fancy word, which is sort of based on the name of the person who created this architecture, but the idea is relatively simple. Right? I mean, in any general purpose program, we have two things. You have instructions and you have data that those instructions process. Right? So that's typically what you would consider a program. The program, instructions and data reside somewhere. That somewhere is essentially the memory. You might know that as DRAM as well in your computer systems. So as you can see here, both instructions and data reside in memory, but these are just dumb bits, right? So your instruction is nothing but a sequence of bits, your data is nothing but a sequence of bits. By itself, it doesn't mean anything. It's all sitting there waiting for it to be interpreted. For all of these sequence of bits to be interpreted, the memory can't do it by itself. So what needs to be done is these set of bits have to be sort of shipped all the way to the processor, where you have a bunch of ALUs, you have a whole bunch of other things that you might have seen in the processor sort of recap course or processor recap part of the summer school. But the idea is relatively simple. The bits that are residing in memory, whether they be instructions or whether they be data, they have to be shipped onto the processors where they are interpreted as being instructions or as being data. And if a sequence of bits is interpreted as being instructions, then it is supposed to do a certain type of job. If a sequence of bits says that it's an add operation, then I need to know which two things that I need to add, or which n things do I need to add, and where do I need to put the result in. Right? So essentially you ship these bits off to the CPU where all the processing is actually being done. The result is produced, and then eventually that is put into memory somewhere. It's not really about where it's being put. But that's where, or that's the general idea about the von Neumann architecture. Right? So how does this sort of fit into the program execution part of the entire thing, which the summer school is all about, right? So remember, what I said essentially was a program is nothing but a sequence of instructions and a set of data that those instructions process. The question is, where is that coming from? So let me just sort of pause here for a bit and just ask if somebody wants to answer this as to where is this sequence of instructions and data coming from that's eventually going to reside in memory of a running program. And as I said, if I don't hear answers, I'll just hold on. All right, so let me start at the bottom. Maybe Rohit. Rohit, you want to take this? Rohit, are you there? Can you hear me? Okay. How about Omkar? Omkar, do you want to take this? Where is this set of instructions and data coming from that eventually resides in memory?
The user inputs it.
Sorry?
The user gives the data and instructions.
So the user is providing instructions and data. Okay, that's, I mean, if you consider the programmer as a user, then maybe yes, but not really. Okay, let me ask somebody else. Maybe Hemant. You want to take this? Hemant, are you there?
Hello, sir.
Hey, Rahul. Yes, go ahead.
The data and the programs are stored in secondary memory, and from when we click on that, then the instructions are loaded into the main memory.
Absolutely.
So
Right?
the data is stored at there.
Yep, absolutely. right? So these instructions or this data is not coming out of the blue from anywhere. Right? So they're actually stored somewhere, and something happens because of which these instructions and data are actually loaded into the memory from where they are brought on the CPU and then they are executed. Right? So essentially, this is the one thing that I wanted to point out is what you consider your program is essentially nothing but a sequence of instructions, which could potentially be compiled as a binary that's residing somewhere on the disk. Right? At some point in time, you say run this binary, which might be as simple as double clicking on that binary, or from the shell you might say / whatever. Right? So that compiled binary is actually read, and it's in a standardized format. So the system, the operating system, the loader, etc., know how to interpret that binary as a sequence of bits. That program is eventually laid out in memory, which again is in a very specific format. So if you look at the address space of a running process, it is in a very specific format where from the low address to the high address, you have segments which are text or instructions. Then you have static variables, the heap, and then the stack. Right? And then they grow in a certain direction, so on and so forth. Right? So the program is laid out in memory. The system knows where the instructions are kind of located in memory, and from that point onwards, your program is in memory, and then the von Neumann architecture or von Neumann model of fetching stuff from the memory, putting it on the CPU, doing the processing and putting it back into the memory, and possibly eventually on the disk as well. And that entire process might be. Right? So essentially, if you think about it, the entire program execution cycle starts right here from the disk where your compiled binary or the program or the sequence of instructions that you eventually want to execute is actually located. And that is why, I mean, again, as I said, a program consists of two things, instructions as well as data. So your compiled binary might be nothing but a sequence of instructions. And then there might be something else over here, which would be the data that these sequence of instructions processes. Right? So these two things combined are eventually sitting on what is your tertiary memory or your storage medium or a non-volatile sort of memory that keeps all of these things together at one location and keeps them intact even when the power goes on. Yeah, that's one of the reasons why it is important for us. So if we really want to understand the program execution life cycle and want to, let's say, optimize the program execution life cycle, then it is very important for us to sort of understand where all of these things are actually going to come from, which is your tertiary storage of storage system. Right? And this is what we're going to focus on in today's, most of it anyways. Right? So again, the final question that I want someone to answer is, okay, you read your binary, which was this thing over here. You read this binary, you laid it out in memory. Your memory has, or your memory layout of the running process has a particular layout, which is shown right here. Right? Okay, so now the program is in memory. What has to be done for the program to start executing? Anybody wants to take that? So imagine that in the life cycle of program execution, I read the binary, I laid it out in memory, and that's where I sort of paused time. Now, what is the next thing that I need to do so that I can actually start executing the program? Let me see, Apurva, do you want to take that? Or is it Apurva? I'm not sure.
Need to assign the resources like input output and the CPU to the program which we want to execute.
Right, so forget about input output. Let's just assume that this is a very simplistic program that does no input output. All it needs to do is run, right? So what does running here really mean? Let me ask somebody else. Hamdan, what does running or what needs to be done from this point onwards for the program to quote unquote run? Sorry, I can't hear you, Hamdan. Okay, Rahul, maybe you want to go next?
Yes, sir. So the instructions are loaded from secondary memory into the primary memory, where they need to be executed one by one to execute the program. So instructions, basically, firstly we allot the memory that is needed for execution purpose. So it may be the firstly the some area is allotted for storing
Right.
the
So that
instruction.
has already happened. Let me just sorry to interrupt, but let me just say that has already happened. Memory has been allocated. The program has been laid out in a specific format in memory. It now needs to execute in the von Neumann style, where things have to go to the CPU. What needs to happen such that it can start? I'm going to put this in quotes because running a program doesn't actually make a whole lot of sense. But still, since that is how we use it, let's go with it. So okay. So everything is in memory. Now what?
So basically, sir, instructions will be running one by one, and the data
Absolutely.
required for those instructions will be taken away, stored and retrieved from the memory.
Okay. So you need to run the instructions. How do you know which instruction to run?
Program counter.
Okay, great. So you've gotten to the point where I wanted everybody to get at is essentially once the program is kind of loaded in memory, you need to know or you need to start executing instructions, which is essentially what constitutes running the program. And which instruction to execute is determined by the program counter. So somebody, once the program is laid out in memory, somebody has to set the program counter point to, let's say, the first instruction of the program, and from that point onwards, it's automatically implemented because instructions have fixed widths. So, right? So anyway, this is eventually what has to happen. So you have to set the program counter, and from that point onwards, it starts fetching instructions at regular intervals, or if it needs to jump somewhere, something like that. Right? So okay, this is what we have sort of studied so far. This was essentially our CPU. This is essentially our memory. And in the von Neumann model, the program is laid out somewhere over here. And it needs to be brought out to the CPU, results calculated, and sent back to memory. It would have been completely fine if there was not a whole bunch of discrepancy in terms of access latency of all of these things. Right? So I'm pretty sure you guys have heard all of these terms in your CPU recap sort of lectures. Registers, cache, DRAM, and then these two are the things that we talk about today, which are essentially the solid state devices and the hard disk drives. And together, they constitute what I'm going to call the storage medium. Right? So, okay. The thing to note here is that eventually everything has to get to memory before it can get onto the CPU. What you can see over here is that the latency differential between stuff that is on chip, which is your registers and your SRAM, and the stuff or stuff that you have to retrieve from memory or DRAM is high, is 2 orders of magnitude, but that's not as bad as things that are essentially have to be brought onto the CPU from something which is tertiary or which is present in tertiary storage, which would take up to a millisecond or so. Right? So what I want to point out over here is that the first thing that you need to remember is that everything is actually going to come from tertiary storage, which is essentially these two things over here. Both of these things combined are approximately 6 orders of, not 6 orders of magnitude slower than how things or how fast things can be processed if they were sitting just on the CPU itself. Right? And because these are the two places, this is the place where everything that you're eventually going to run is going to come from. It's imperative that all of us kind of understand, how this last stack or last part of the entire computing system concept is actually architected and why or how it actually works. Right. So before we get into the architecture of these things, let me just quickly point out that this is, or storage is also known as persistent storage, and all the kind of architectures that we look at today are essentially the ones that are going to be persistent, which essentially means that if I pull the power plug, the information that is on the medium is going to stay on the medium. This is very different from things like your caches or things like your memory, where if you pull the power plug, whatever information is there in your caches or in your DRAM essentially just vanishes all of a sudden, right? There are two types of storage media or two types of devices that are mostly used today. One are the hard disk drives, and the other one are the solid state devices. And we look at the architectures of each one of these things separately. Right now, most of the traditional client-based devices that you might get today, for example, if you buy a medium-ish end laptop, it doesn't even need to be a high-end one. It would typically come with an SSD, right? So the question that I get a lot of the times is, why are we even bothered about hard disk drives today, or trying to optimize hard disk drives when everybody sort of clearly knows that that solid state devices are the ones that are being used in most of the things that you see around your smartphones, your laptop devices, even sort of decent high-end desktop devices have SSDs. Right? But what we need to remember is that the bulk of world storage today is still stored on hard disk drives. So if you go and look at Google's or Facebook's data centers, although they have some amount of solid state devices that are there for performance reasons, but the bulk of their storage, your photos, your other things that you sort of, or videos that you took 5 years ago that you don't watch anymore, are the ones that are sitting on a hard disk drive today, somewhere in some data center. And that's why it's also important to understand why these things, or how these things work, right? And the idea there is that if we understand how these things work, we might be able to optimize not just these specific components, but also the software stack that kind of builds on top of that. For those of you who don't know, Jim Gray is a very famous researcher at Microsoft Research. And then I think in 2006 or 2005, he gave this excellent talk where he talked about how the storage media is going to evolve over time. And so far, his predictions have been sort of right. Right. So again, whenever you get the time, go look up. This is the title of the talk. Go look up that talk by Jim Gray from Microsoft. Right. So moving on, let's quickly talk a little bit about how hard disk drives are actually structured. Right. So if you sort of pull up the cover on a hard disk drive, this is the set of things that you will see on there. Right. And we'll take a look at each of these things, or at least the major portions of the architecture of a hard disk drive, and sort of get a sense of how this thing actually works. Right. So if you look at this part of a hard disk device over here, this is where it connects to the outside world. Right. So you would have an IDE connector or a bus-like thing that kind of fits into this slot, and that connects this device to your computer system. Right. And then at this point in time, we're not concerned with how data is coming in and out of the device right now. What we're concerned with is how this device itself actually functions. As far as the architecture of the device is concerned, there are a few main components that we need to understand. There is this sort of plate-like thing which is called a platter. Right? This is where your data is actually stored. So think about it as a disk on which there is magnetic material that's coated right here. So this is the surface area of this disk or the platter, and there is magnetic material that is coated onto the platter, and this magnetic material is capable of storing information as zeros and ones, and then you can also potentially retrieve that information. In order to be able to store or retrieve that information, you need to go to the right area on the platter where your information is stored and sort of read what information is being written there. But now, as you can imagine, this is a circular medium, right? So you need something that can sort of go to the right place on your hard disk drive and sort of look up, read or write the information that you need to be read or written. This thing is actually done by what is known as the actuator arm. So this thing right over here is what is known as the actuator arm. It is fixed right here, and it can move on an axis like this. Right? So your actuator arm moves on an axis like this, and this way it goes back and forth, and it can cover the entire sort of radial area of the disk. Now, to go to any portion of the disk, the actuator arm can't travel all the way to, let's say, over here, right? It can just go back and forth. In order to make that happen, in order to make the entire area of the disk coverable by this one actuator arm that is fixed at an axis, what happens is that this particular disk, which is your magnetic material, it spins at a very high rate per minute, which is somewhere around 7,500 to 15,000 revolutions per minute. Right? So imagine this disk is spinning very rapidly, and imagine that information is stored in some fashion. I'll get to that how that is actually stored in some fashion under that disk. If you know where information is stored, all you need to do is to make sure that the actuator arm sort of goes to the right location. And at some point in time, after the disk has done some amount of rotation, that region will come right under the actuator arm or right under what is known as the head of the disk. And the head of the disk is configured to read out the information from that particular. Right? So that's typically how the hard disk drive works. Right? So imagine you have a bunch of these platters. These platters are coated with magnetic material. You have one sort of thing over here, which is the actuator arm. It has a head at the top of it. The head is capable of reading or writing information onto the magnetic material. In order to be able for this head to be able to access each and every region of the platter. The platter is spinning at a very high frequency, and the actuator arm, depending on what other commands are given by the user, it can sort of position itself at the right place on the platter, and from that place, it can kind of read and write information. Right. So that at a high level is how hard disk drives work. But let me just quickly sort of give you a sense of how information is stored over on these devices as well. Right. So we've talked about magnetic disk, which is called a platter. Right. So the platter can have or magnetic material coated both on top as well as at the bottom of it. Right. So that gives you twice the amount of capacity that you can potentially store on one given platter. But it also results in a whole bunch of other trade-offs that we might not have the time to talk about. But anyways, think about, for the time being, platter with magnetic material on just one side, but potentially it can have on both sides as well. Now, in order to be able to store information, I need to be able to address each and every location. Right? So, for example, if you think of memory, if you're trying to access some information located in memory, what you eventually end up doing is you say, I want to read this from this address, or I want to write this from that address. Right? So your address serves as the point to which you have to go to read or write information from. You can imagine something similar is needed for hard disk devices as well. So we need some mechanism by which I can say, okay, I need to read this file, but this file starts at this location on my hard disk drive. Right? So in order to be able to arrange information, what is typically done is you have these things which are essentially concentric circles on a given platter that are called tracks, and then tracks are eventually divided into sectors. So let me sort of just quickly give you a diagrammatic representation of what this works. So again, imagine a hard disk drive. There are multiple platters in this hard disk drive. So this is, let's say, platter 0, this is platter 1, this is platter 3, this is platter 2, so on and so forth. Right? So each one of these platters has a magnetic material, and let's for the time being just also assume that there is only one side that is coated with magnetic material, which is a transistor. Now, each one of these concentric circles are essentially called tracks, right? And each one of these tracks is divided into what is known as sectors. So if you have this delta or sort of like a pizza pie slice thing coming out from the center of this platter, then you have a sector on each and every track, right? So if I have this, if I look at it from a top view, this is my platter. There's a whole bunch of tracks on this platter, and each one of these tracks essentially has a sector. So if I want to sort of locate some information, I can say this information is located on platter 0, track 25, sector 35 on that particular track, or on that particular platter. Right, and that gives me a way to get to that particular location and get the information. And then typically that's how most of the hard disk drives work. Now, if you have multiple platters on your hard disk drive, then you can say, well, my information or a portion of this file is not just located on platter 0, but also on platter 1 or also on platter 2, also on platter 3, so on and so forth. And then somebody, and this is something that we get to when we talk about file system, somebody has to sort of keep track of where all is your information spread across. Right? So if you have a very large file, right, then it might be spread on some tracks on platter 1, some tracks on platter 2, some tracks on platter 3, right? And then different sectors on each one of those tracks as well, right? So when you say read this large file, your file system essentially sort of keeps track of where all of this information is stored, on which tracks and which sectors, and depending on which portion of your file you want to read, sort of converts those read and write commands into disk-specific commands, which essentially tells the actuator arm to sort of go to this platter, to this track, and start reading out these many sectors. So this is essentially how bulk of the hard disk drives today work. Right? Over time, one of the ways in which manufacturers have been adding capacity to these drives is by two ways. One is by making sure that you can read and write, or you have magnetic material coating on both sides of the platter. So that gives you twice the storage capacity. Also, you can increase the number of platters, right? And again, there are trade-offs over there because, as you can imagine, these platters are spinning at very high frequencies, and they might sort of crash into each other if there are too many of them. Right? So, okay, so there are sort of reliability issues with having too many platters as well. Right? Okay, so now let's talk a little bit about where is the latency of a disk access going to come from. Right? So imagine if I have to read some information from the disk, what has to happen is I need to go to that particular platter, or I need to position the arm such that the head is on a given track of the platter that I want to go on. And then I have to wait for the disks to spin such that the right sector comes right below the head. And only after that is when I can start reading out the information, right? So there are multiple sort of components to disk latency or hard disk drive latency that I've kind of listed out over here, right? So the first one is what is known as seek latency, which essentially is what is the time it takes for the actuator arm to go to the right track, because it must have been somewhere else doing something or some other read or write. So it has to sort of go to the right place before it can start reading information out. So that is the seek latency. The rotational latency is, okay, now I'm on the right track, but I have to wait for the right sector to come right below me so I can start reading information. Right? So that is the rotational latency. And the transfer time is once you have sort of gotten the right sector right below you, then there is some amount of time that it takes to read the information out. And that's typically what's known as the transfer time. And then there might be other overheads as well. So this is just the amount of time it takes for you to read the information out of the media. And now the media has to be transferred over the IIT connectors to wherever, let's say in memory, this media needs to go, or this information needs to go, right? In the interest of time, let me not talk about cylinders, but as you can imagine, if you have multiple platters, in order to be able to reduce the amount of time it takes for you to seek a particular location, what you can potentially do is store information in such a way for, let's say, large files, such that your seek times are minimized, right? So if I have multiple platters, what I can think about is I'll have, let's say, track 35. Let's say this highlighted track is 35, and I'll have a track 35 on all of these 4 platters, right? So if my file is large enough, what I can do is I can split that file on track 35 if space is available over there. What this allows me to do is position. So one thing that I'll just quickly mention over here is that if you have multiple platters, then all of these actuator arms are still connected to the same sort of spindle, and they move as one unit, right? So even if you have 4 platters and 4 actuator arms, all of these 4 actuator arms for these 4 platters move as one unit, right? So if you position one on track 35, the rest of them are automatically positioned on track 35 for the rest of the platters. And if that happens, then it makes a lot of sense for me, me being the operating system or the file system, whoever is trying to split information on the hard disk drive, to split the information on the same track across multiple platters, right? Because once I position it on one track, the rest of the handles are automatically, or rest of the heads are automatically sort of positioned onto the rest of the tracks, right? So, okay, that's one potential optimization that you can do to reduce the overall seek times, right? I mean, you can go back and think about what would have been the counterfactual for this, right? If this was not the case, then what would have happened, which would have actually increased seek times. That's just a good trade-off design exercise that you might want. I kind of embedded this video over here, but I don't think I have the time to go through this, but I'll share the slides. And this is a very nice video in which the person who's created this video has removed the top of the hard disk drive and has just done a whole bunch of operations, and you can see a lot of things that are being done in action in this device. So I'll really encourage you to go and see this particular thing. Right. So now a few things that I really wanted to talk about was, because you have mechanical moving parts, you have this actuator arm that has to move back and forth and at very high frequencies sometimes to be able to sort of do your reads and writes. This is what contributes to the slowness of these hard disk drives. It also makes them very unreliable. Right? So sometimes when you say your hard disk drive has crashed, what that literally means is that your head, which was sort of hovering on top of a platter, has actually crashed into the platter. Right, and it can't move anymore, and that's the origin of the term that my hard disk drive has crashed. Right? You can't retrieve information from that anymore unless you kind of replace that head, which sometimes is possible, sometimes it's not. Again, going back to what I had just talked about earlier, are disks becoming irrelevant? So there's a white paper from 2016. Again, this is 5 years ago, and things change very quickly. So take whatever is written over here in with a pinch of salt. But then what Google essentially thinks as of 5 years ago is that the demand for hard disk drives is not going to go away, especially for data centers. Right? So again, I really encourage you to go and sort of look up this one. Okay, so this is something that we have talked about. Right? So we've talked about what seek time is, I talked about what rotation delay is, and there is amount of time that is taken to transfer the information from the device. There are some other things that contribute to the latency as well, but they're not as time consuming. For example, command issue or the stabilization time, but these are not very or large enough to be able to contribute significantly to the distance. Okay, so how can hard disk drives get better? You can improve interconnects. So the amount of bandwidth that's available to transfer information from the device to the rest of the system can potentially increase. You can improve seek times. One of the optimizations that I just mentioned was storing information across multiple platters in cylinders, so that you have reduced seek times for seeking the overall amount of information that you need. Rotation speed. So again, you can make sure that your disks are rotating as quickly as they can. They have kind of peaked around 15K, because then again, if you spin them any faster, there are reliability issues that come into play, and you don't want that. Right? Okay, this is one thing that I just quickly wanted you to sort of take a look at as well. This is time on the x-axis. Y-axis is what is known as area density, which is the amount of bits that you can store per square inch. Right? So as you can imagine, as your areal density grows, the same amount of area could allow you to store more and more bits. And that has also grown very quickly over time. Right? So because of the advances in the way material scientists have come up with the materials that can store more and more bits per square area, that's one of the other reasons why your hard disk drives have become larger and larger in capacity. And similarly, over time, the prices have also fallen. So again, y-axis or rather x-axis is years, y-axis in this case is time. And again, this is a combination of memory and disk and flash devices. And as you can see, it has this is the interesting area that concerns hard disk drive. As you can see, it has come down very, very quickly. Amount of money that you have to spend for storing few bits of information. Right? So it's become very, very cheap. There is some more innovation that is happening in hard disk drives, and again, this is to increase the capacity that can, again, to increase the areal density to some extent. Up until now, what I had talked about was there are these tracks that are there on the platter, and then there is some amount of gap that is being provided between the tracks, just to make sure that you're not overlapping between tracks and you have enough sort of safety margin, so as to make sure that you're reading the correct information. And again, with clever material scientists, clever mechanical engineers, what people have been able to do is reduce this gap and are able to sort of, to some extent, lay these tracks on one top of each other. Right? So as you can see over here, these tracks somehow, if they can be placed on one top on top of each other, and the amount of band gap or the amount of safety region that you need between tracks can be reduced, then you can store more information on that platter. And that's exactly what has been happening with what is known as SMR, or shingled magnetic recording discs over there. So again, this is an innovation in how information is stored in the magnetic material, arranged and stored in the magnetic material of the platter itself, and that has helped increase the capacity or areal density over time. Right? Okay. So this is all I wanted to talk about hard disk drives. What I'll do is I'll quickly give you a sense of SSDs as well, because I think we have like 12, maybe 15 minutes left in this lecture. So I'll give you a sense of SSDs as well, and then maybe take all the questions towards the end as well. Right? Okay. Excellent. So SSDs are built on a technology which is known as flash. So I'll talk a little bit about flash, specifically NAND flash. Right? And this is not a new technology. It has been around since the 80s, even earlier than that if you just consider prototypes. Right? But it's been only lately in the last 10 years or so that there has been an increased availability of these sort of devices on different kinds of compute devices. These kind of storage devices on the compute devices that you see today. Right? So the sudden increase in interest is because of two reasons. One is hard disk drives were not scaling up in terms of decreasing latency. Right? So the amount of time that it takes, or the minimum time that it takes to read some information from a hard disk drive is dependent on how long it takes to position the mechanical moving parts, and that can only be decreased by so much. So you can never kind of go beyond, let's say, the millisecond range latency for a hard disk drive. Now, if we so that's point one. And the other point is that the form factor. So these are spinning media, and you can't compress them too much. Right? I mean, if you want high capacity and highly performant disks, they have to be of a certain form factor. And if you look at things like, let's say, the MacBook Air, you can't really fit in these thick form factor spinning media in there, because what you eventually want out of the product is something which has a very sort of a thin form factor. So you need to go to something, or you need to find a technology that essentially is not dependent on mechanical moving parts. Finally, at some point in time, the economics of large scale kind of came into play for flash devices as well. And at some point in time, they became relatively affordable in terms of cost per gigabyte. So around 2008, if you look at SSDs, they got, and again, this is relatively old data, 7 to 8 years old. So just take it with a pinch of salt. But from $40 per gigabyte, they came down to around $1 per gigabyte around 7-8 years ago. Right? So this became really, really affordable, and it is around the same range as hard disk. Right? So this is, let's say, a better performance, a better performant medium, and it is relatively also very cheap, or relatively affordable as compared to hard disk drives as well. And that is why people said, well, okay, let's start sort of incorporating more of these things in different kinds of computing. And again, I don't need to sort of tell you about how the data generation rates have been increasing over time. So not only you need to sort of look up your information quickly, you also want to look up large amounts of information quickly. Right? And that is also something that was being bottlenecked by hard disk drives because of their rotational reasons. Right? Okay. So if you look at NAND flash, what it is made up of is it's fundamentally different from how it's fundamentally different in how it stores information as compared to hard disk drives. So a flash cells stores information as essentially charge in a game. Right? So if there's a small amount of charge, you can construe that as a 1. If there's a large amount of electrons over there, you can construe that as a 0 or vice versa. Right? But then again, it's sort of sensing how much charge there is, which is similar to how DRAM devices work. Right? So as you can imagine, if I want to figure out whether what is stored in this cell is a 0 or a 1, I need some circuitry to figure out, how much charge is there in this gate, which is very different from, oh, let me just move this actuator arm to that location and then sort of read out this information. Right? So now you can imagine in the best possible case, I can read information at the speed of light, so to say, or as fast as I can sense how much charge is there in this cell. Right? So because flash fundamentally works this way, as a storage medium, as compared to magnetic platter-based hard disk drives, is fundamentally faster because of this. Right? So and it depends on how much threshold voltage you apply, which determines how much charge can be stored in that gate. Right? So if I have this spectrum over here where the threshold voltage goes from some value to some value, right? I can sort of break that range at a reference level and say anything below this is going to store a specific amount of charge, and that is how much charge is being stored over there is also sort of governed by a probability distribution function of some sort. But what I'm going to say is anything that's any amount of charge that is below this certain threshold, I'm going to consider as a 1, and any amount of charge in this cell which is above this threshold is essentially going to be interpreted as a 0. Right? And that forms the basis of almost all flash cell technology that you see today. This can also potentially give rise to higher storage densities by doing certain optimizations which are like this. Right? So in the previous slide, what I said was, here is this y-axis is a range of threshold voltages, and I somewhat arbitrarily said from this point onwards everything is a 1, and below this point, or from this point onwards everything is a 0. Below this point everything is a 1.
Hi. Sorry to interrupt. Why is it okay if I ask a question?
Could you just hold on? Maybe I'll just
Sure.
sort of go over. Yeah.
Sure.
So
thank you.
excellent. And one of the ways in which you can increase your density of how much information you can store in one given cell even is by arbitrarily setting more thresholds. Right? So I have this threshold voltage range, right? And then I sort of arbitrarily set 3 thresholds over here. And what I say is anything between this, the lower range and this point over here is going to be construed as 2 bits, right? A 1, 1. Between these 2 places, it's going to be construed as or interpreted as 1, 0. And between these ranges, it's going to be interpreted as 0, 0. And between these 2 ranges, or this range and the higher range, is going to be interpreted as a 0, 1. So rather than breaking this range into 2 sort of pieces, which was going to be a 0 and a 1, now I'm breaking this into 4 pieces, and each one of these ranges can be associated with 2 bits of information. Now, 1, 1, 1, 0, 0, 0, 0, 1. Right? And you can imagine I can sort of keep on doing this ad infinitum. Right? I mean, I can keep on breaking this range into multiple ranges, and then I can associate each range with 3 bits of information, 4 bits of information, so on and so forth. And that is essentially what is known as a multi-level cell. Multi-level cell typically in most technology parlance means that you're storing 2 bits for whatever reason. A 3-bit or 3-level cell is essentially something that stores 3 bits. And 3 to 4 bits per cell is something that has actually been demonstrated by multiple people. It's not available commercially, but MLCs are available commercially, right? Okay, so so that's how information is actually being stored as essentially the amount of charge that is there. Now, there is fundamental limitation with the flash technology itself, right? What you can potentially do is you can, if you have a group of cells, so you can imagine if you wanted to store a bit string, you can connect a bunch of these cells in, let's say, series, and then read out all of these cells to figure out this activity information. Now, the fundamental sort of drawback, let me call it that, of flash cells is that you can convert a 1 to a 0 relatively easily, but to go from a 0 to a 1, you have to first not only, or you can't just do one cell in one go, right? You have to take all of these cells and have to convert that into a 1 before you can sort of change any one of those zeros into a 1. Right? So essentially, that's what is being said over here, is that if you want to set back to a 1, an entire group of cells need to be reset. Right? And that is just how sort of Flash has been architected over time, which has sort of given rise to this drawback. And that is one of the reasons, or one of the biggest drawbacks, which complicates SSD design to some extent. Right? So in order to be able to, let me just go to this particular slide, and hopefully it will help you sort of understand or put things first. Right? So in order to be able to read or write, or reading is relatively easy, right? And if some information is written into a group of cells, I can read that information out. Now, if information has to be written or overwritten, let's say, into a given cell, what you need to do is you need to do what is known as a erase operation. So you saw that sequence of cells that were connected together. Those sequence of cells together form what is known as a page. Page is nothing. I mean, this is different from page, what you've heard of in paging in memory. But this is a page in the context of an SSD. And what's happening in this case is nothing but a logical arrangement of a group of these cells that we saw before. Right? So I have a page of information, which is typically, I think, around, let me just quickly go back. A page is typically 4 to 16 KB. Right? And this page is made up of multiple blocks, which are 128 KB or some multiple of them. Right? So I have a group of cells or flash that are connected together. These group of cells can form a block. A bunch of these blocks form a page, right? And that's typically how the SSD or the internals of an SSD is logically kind of architected, right? So if I want to read information out of an SSD, typically it is done at the granularity of a page. Right? And again, that is true for storage devices in general. You typically don't read 1 bit or a few bytes out of a storage medium because they are so slow as compared to the rest of the system. What you typically try to do is make sure that you are exploiting as much locality as is possible. Right? So you typically read out a larger granularity of information. In the case of an SSD, that larger granularity of information is a page, which is, let's say, around let's say 256 kilobytes worth of information, right? And then to read any page, you can just sort of say that I want to read this particular page, and there is nothing special that needs to be done. Reading is relatively straightforward. It is very, very fast, takes around tens of microseconds. Part of that has to do with the fact that you're reading a large amount of information, and part of that has to do with the fact as to how that information is actually arranged within the SSD itself. Right? Now, things become a little tricky once you sort of have to write information. Now, because your SSD is sort of arranged in these blocks of information called pages, before you can write, and you write information at the granularity of pages as well, right? So if you have to write information, you have to write, let's say, 256 kilobytes worth of information. Before you can write information in any location, that page has to be first what is known as erased, right? So essentially the cell has to be taken, or the set of cells, storage cells that constitute that page, has to be taken into a special state, right, such that you can write the information that you want, right? So that entire set of cells has to be programmed to all ones, which is essentially sort of like cleaning the blackboard, right? And writing all ones over there. Now, some of these ones you might want to flip to zeros, and you can only flip a 1 to a 0. You can't go the other way around just because of Flash's limitations, right? So before you want to write information, you have to sort of erase a page, and pages have to be erased, or they have to be erased at a larger granularity, which is again 256 kilobytes or so, right? So entire page must be erased. Then only you can write information onto that. And programming a page is nothing but sort of writing the information, right? So if I wanted to sort of just show this diagrammatically, think of this block as your SSD, right? Your SSD, again, this is a logical view of this entire thing. So your SSD is divided into a bunch of these things, which are pages, right? Pages by themselves. So there is a set of information, or there are a set of pages that contain useful information, and let me just mark them with a green. So this is a page with useful information. This is a page with useful information, so on and so forth, right? And let's say these are the 4 pages that constitute your one file. Now let's say you want to write some information at some location, and you decide that, okay, this is the page that I want to write that information in. This page has to be first. So I need to do a write. Right? Before I can do a write, I have to first figure out where I want to do that write, which I have already done, which I have figured out that this is going to be the page that I want to write. The next thing that I want to do is, or that I'll have to do, is erase whatever is there in the page, which essentially sort of sets itself, or sets the page up for the eventual write of the information that's going to happen in that page. So I'll say that I want to do this has gone away, but just quickly draw this. So I have my SSD that is logically divided into these things. I want to write to a page. For that, I need to first erase the page, and then eventually write information into the page. Right? So in-place writes are not really possible. So if you, let's say, you wanted to change one bit in a page, right? Your page is, let's say, 56 kilobytes, and you wanted to change one bit in a page, what you eventually have to do is you'll have to read out all the information that is there in the page, right? You read that out into a buffer somewhere. You sort of change that one bit that needs to be changed, and then you write all of that information back into some other page somewhere on the SSD. And that is what sort of what complicates the architecture of the storage device, right? So if you look at the architecture of an SSD, which is essentially this part over here, what you'll see is a whole bunch of these things which are known as flash memory packages, or flash packages. And if you sort of look at an SSD, these are the black things that are sitting on the PCB. Within these flash devices, so there are multiple of these flash devices or flash packages that are there. Within these devices are a whole bunch of pages that are there that I had just talked about, right? Your information, let's say your file, is divided across, or is written across possibly multiple pages, and these pages could be located across multiple memory packages as well, and it's a function of how things, or what are the policies that are set by the SSD manufacturer, right? Right. So if you look at the SSD, let's say you want to do again, I'll take a simple example. Let's say you want to do a read, right? If you want to do a read, you send that set of read commands from your application or your intent to read from your application goes to the SSD. Your SSD has a processor, and this is mostly present for bookkeeping operations. As I said, you have to keep track of where information is being stored, which are the pages within your SSD that are actually useful, which are the pages that are in a non-erased state and have to be erased before you can actually write information over there. And that is then information that sort of needs to be processed. So when people say, I'm going to upgrade the firmware or there is a firmware that's running on the SSD, that is the piece of code that is running on the processor within that is present within your SSD itself, right? So this set of read commands that you wanted to do goes to the processor. What the processor does is sort of looks up what is known as the flash controller, which has something which is known as the flash translation layer, right? And this is similar to the mapping of your information to a platter, track, sector in your HD, right? So in this particular case, this flash translation layer or FTL essentially takes the read commands and figures out, okay, you wanted to read, my word file.txt, and this my word file.txt maps to this particular page over here on this package and this particular page over here on this package, and sort of sends out the appropriate commands to those pages, gets the information, sends it back, and then it's eventually sent back to the application. Right? Similarly, for a write path, it's a little bit more complicated because now you have to kind of figure out where it is that you have to write and which page has been erased and or not been erased, and so on and so forth. Right? But hopefully that gives you a sense of how SSDs are kind of architected. So I think do I have more slides? Let me just quickly see. Okay, I'll quickly mention one more thing. Right. So we've sort of talked about SSDs and HDDs. Then the question becomes, what do I use and where do I use them? Right? So are there certain cases where HDDs are better? Are there certain cases where SSDs are better? And it's a combination of a lot of factors. But the single most important factor is essentially the behavior of your workload. Right. So the behavior or your application would say, what I expect out of all my reads and writes is for them to complete within this sort of window of time, right? And your application would also send out a sequence of read and write requests that essentially either look random, right, which is essentially similar to pressing sort of random keys on a keyboard, or they might look sequential, which is similar to pressing, sequence of keys, 1, 2, 3, 4, so on and so forth. Right? A very good example of a sequential workload is a movie file. Right? So if you look at a DVD, your information is stored as frames, as consecutive frames in consecutive locations on a DVD. So your DVD reader is a relatively simple entity. All it has to do is it has to start at where it needs to start, and then it can keep reading successive locations because all it needs to do is read out one frame. Right? So the one thing that I kind of also wanted to impress upon you is each one of these sort of types of devices have their own pros, have their own cons. Which one to use is a function of, which one to use where is a function of what your application is trying to do, what its requirements are, the kind of requests that it generates, whether they are sequential, whether they are random, so on and so forth, and what are the windows in which it expects these requests to be completed. Right? And based on that, you can sort of either use an HDD, you can use an SSD, or you can use a combination of those two, which is also something we'll hopefully be able to touch upon later in the day. Okay, so these are excuse me, sort of larger takeaways from this 1 hour. The architectures and the storage technologies on which each one of these devices are based are fundamentally different. Have been optimized for different things over time. Both are here to stay. Hard drives are here to stay, at least for the time being. And again, just because we know the underlying architecture, hopefully we'll be able to use this information better when we're trying to optimize the upper layers of the software stack, which essentially is the devices or even the applications for them. Right? Okay, so I'll quickly stop here and I'll take any questions that you guys have. I think you had a question.
Yes. So I have 2 or 3 questions. The first question is that why do we consider a charged cell as 0 and an empty cell as 1?
Or, I mean, it's just a matter of convention. You can do it whatever. So you can do it the other way around, and it'll be exactly this way.
Yeah, I mean, obviously convention is there for a reason, right? This must be relating some way to the sense amplifiers or to the,
Not really.
I mean,
I don't think
no?
so. I mean, there are a lot of conventions that are there just because of historical reasons. They don't make any sense anymore. But, for example, 4 kilobyte page size. Right? 4 kilobyte page size is there because it relates to what was the block size on the hard disk drives a very long time ago. But then we kept building on top of that over time, right? And maybe it makes sense still, maybe it doesn't. But the reason that 4 kilobyte number has kind of stuck around is because of historical correlations.
Yeah. Okay. Thanks. The second question would be that, yeah. So this was like a very overview of this, but what is exactly happening at the device level? Like, what is this device and what is the operation that we're performing on a particular device? For example, for DRAM, you have these capacitors, right? Capacitors store charge and then you discharge them. So in case of flash, what is the underlying device which is storing the information?
It's a NAND flash cell. I mean,
And
again,
yeah.
it's an operation similar to a DRAM, or rather DRAM charge or discharge. But essentially, at a relatively high level, what you have to think about is you apply a voltage and some amount of charge gets stored. Right? And depending on how much voltage you apply, that's the amount of charge that gets stored. And basically, that's it. I don't know if, I mean, I don't know enough about how exactly the devices work to be able to give you a detailed answer.
Manu, can I pitch in? Ashish here.
Yes, please. Yes.
Okay.
Absolutely.
So actually, that basic device Adi, is a field effect transistor which has a floating gate surrounded by an insulator. So as Manu said that you apply high voltage. So when you apply high voltage, then there is what is called as hot injection method, by which the electrons, they cross the insulator, and this floating gate is actually a conductor. So they get accumulated on the conductor, and then you remove that high voltage. So as a result, because it's surrounded by insulator, they cannot go back, and that's the reason why it is non-volatile in the nature, that once you store that charge, it remains there. And as a result, what happens is, suppose, assume to begin with, there is no charge. So this FET acts like a switch. So the gate controls connection between source and drain. So now this is a normal behavior, and when this happens, then this is treated as 1 because the switch is operating. So that also answers your question about why that is 1. That is, no charge is 1 because the switch is operating. However, when you have this hot injection method, because of which the charge is collected on the conductor, it becomes like a battery which is opposing the voltage of the gate, which is supposed to connect source to drain. And when this charge is accumulated, it cannot allow the switch to operate because that small voltage is opposing the voltage that is applied by the gate. Hence, this becomes a 0. So that's why it is, as Manu said, that when you get it a fresh E square prom or a flash, you read all once because all the switches are operating, because the gate is having effect on source and drain. But selectively, you can deposit the charge through this hot injection method. And that is how, and if I'm not sure your generation has ever seen an EEPROM, but there used to be something called as erasable programmable memory with Manu might have seen it. It had a window. It was in a ceramic casing. It had a quartz window through which you could bombard it with 20 angstrom unit wavelength UV rays, and the charge would get, it would get erased. So that is the basic idea. But soon there were two scientists, Fowler and Nordam, who came out with a method by which this could be done electrically. So this is at the microelectronics level, and we don't have time to go into that. Neither do I have complete knowledge to tell you. However, to compare a capacitor in a DRAM, the equivalent of that is a FET, field effect transistor, with a floating gate embedded in an insulator. Over to you, Manu.
All right. Thank you very much, Ashish.
That was very interesting. Thank you, Mr. Ashish. Yeah, that was the answer that I was looking for.
Okay, excellent. Any other questions?
Yeah, I have a question.
Rahul, yes.
So, like, as Adi was saying, like, why do we have this nomenclature like zeros are ones and ones are zero? So, it feels like, as you said, that it is difficult to go from. It is easy to go from zero to one, but difficult from one to zero. So isn't it like we stored our data in a reverse format, like all zeros are stored as one and ones as zero, and then we put an inverter just to save something, like save power, as for to charge the cells to one, it will take some more power to charge it, and we store it in a different way, and then use something else to get the correct data. So isn't it something like that?
Right. So what you're saying is essentially a mechanism or a scheme of how to store information, right? So what you're saying is just flip information if it makes more sense, and then when you are sort of giving that information back to the application, to the operating system, flip it back again.
Yes,
Right?
so just like if we have a data of 32-bit and all are ones and except two threes are zeros, so why don't we store it in all our zeros except two three are one to save our power, and then reverse it using inverter and all to
Right.
get
So
the
I
correct.
mean again, right. So the again the info or the mechanism that he used to store information, right, or the coding scheme rather that he used to store information, can be basically anything that you want, right? And almost all of that has been determined by empirical evidence to some extent, right? So, for example, like Ashish was saying, um, you have to sort of program the cell to all ones, and then you or rather erase the cell to all ones, and then you can selectively change them to zeros, whichever one you want them to be zero, depending on what data that you have to read. Right now, it's purely a function of what is the type of or what is the sequence of bits that you want, or that your application or sequence of applications or whatever it is that that are writing to your medium, right? If it's such that you only have to flip a small number of ones to zeros, then it makes sense to keep the coding as is, right? So you information as is and then read it as is. Whereas if your set of writes or the information that you're trying to write to your medium is such that a lot of ones are being flipped to zeros, right? Or a majority of the ones are being flipped to zeros, then it makes sense to store the information in an inverted fashion. Have a bit somewhere that tells you that the information is stored in an inverted fashion. And when you're reading it out, you kind of invert it back again
Yes.
to some extent. And
Yes.
okay, so, and that is to some extent done in other contexts, right? So, for example, places in where the lifetime of the cell, for example, in non-volatile memories, which we might talk about later on, the lifetime of the cell is dependent on which value you are writing more frequently. Right? So if you're writing one more frequently or write zero more frequently, at some point in time, you might sort of destroy that cell. Right? So depending on that, you write either the actual value or the inverted value, right? Depending on how many times a particular value has been used. So those kind of um, mechanisms have been employed. I just don't know if they have been employed for the reasons that you're talking about in modern SSDs. But I'll look that up. That's an interesting point. I don't know if that sort of a information coding theory approach has been applied, but I wouldn't be surprised if it has.
Yeah,
That's a good
yes.
point.
And one more question I have is that, like you said, that we need to, if we want a faster memory, we need to improve our interconnects also. So why interconnect plays a role in the memory? Because we have a memory and we have a magnetic disk, and it runs and it get data. So this is what takes time, right? Interconnect will transfer it with whatever speed it has from any level of hierarchy. So why does it need to be
Right. So
like?
I mean, for example, I'll give you a sort of a different example. Right. There are these set of devices called NVMe SSDs, which have been architected in such a fashion such that they are capable of giving very high bandwidth and very high random input-output operations per se. Right. Now, let's say they are capable of giving you a million random input-output operations per second, which translates into some amount of bandwidth, or let's say translates into a gigabyte per second of bandwidth, and that has to come out of your device, right? Now, if this very sort of fancy storage device was hanging off of a crappy medium, right, or a crappy interconnect, let's say IDE or SATA or whatever, even though the device itself is capable of giving you your million IOPS and a gigabyte per second of bandwidth, the application is not going to see it because now the interconnect, the stuff that connects your storage device to the rest of the system, is now the bottleneck. So your pipe becomes the bottleneck, and that's why interconnects also matter eventually. They might not matter as much for hard disk drives because, I mean, you can't really go that fast, right? So even if you hang hard disk drives off of SATA or SAS, you're okay. 250 to 800 megabytes per second is probably the maximum that they could give you as a device itself. But if your device became much more capable, then your interconnects need to sort of scale up appropriately. I hope that makes sense.
Okay, sir. Yes. Thank you, sir.
Rahul, you had a question?
Yes, actually my question is purely based on experience that some of my friends had a very strange experience that consider the setup that they are having in their PC. So they are having one 250 GB SSD and 1 TB HDD. Okay, and SSD is having their Windows operating system installed in it, and by default they are having only that operating system installed. Afterwards, when they wanted to side boot with Ubuntu, so they did that. They installed the Ubuntu inside the HDD, not in the SSD. But what they got very strange experience that their SSD became slow. Eventually, their Windows became slow at some extent.
Hmm.
So, would you like to add any thoughts on that?
Um, I mean, that really shouldn't happen. Um, that, well, it's a function of what the SSDs are being used for, right? So most of these devices that come in with, or on most of these computer systems that come in with two devices, an SSD and an HDD, they kind of use it in various fashions. Some of these, and again, that's probably a Windows setting to some extent. It could be using the SSD as a cache for, your HDD is your primary storage medium, and SSD is being used as a cache to some extent, and except for keeping the operating system image or something, right?
Yeah.
Or it could just be using that as a tiered storage, right? So your quote unquote most important files go into your SSD, and your not important files go onto your HDD, and that is sort of like the tiered storage structure. Now, if it could be possible that because of the installation on the hard disk drive of Ubuntu, and however it was seeing the system as a combination of SSD and HDD, the SSD that was being used as cache somehow got full, right? And
Yeah.
now just looking up information on the SSD takes potentially longer, right? Because these FTLs that it has to go through, it has to sort of, let's say, look up larger data structures. It takes time to sort of traverse those data structures. So again, I don't know what that SSD was actually being used for. At face value, it doesn't seem like it should be the case. But then again, depending on how those two devices are configured to be used, um, unpredictable results might happen.
Yes, actually, Ubuntu might be using that SSD for any other purpose. That's actually makes some sense. That might be the reason.
Cool. All right. So let me just quickly check when is the next session supposed to start. Okay. So we're supposed to start at 11:30. It's already 11:25. So maybe we'll take a 10, maybe 15-minute break, and then meet again at 11:40. Let's say. Is that okay? All right. So let's start at 11:40 again.
Yes, sir. Sir, I had a question like
Sure.
the write operation in SSD, is it costlier than the one in HDD or because the read is faster on SSD than a HDD? So write has a lot of limitations in SSD. So is it faster in HDD or because of that limitations is it slower than
No.
HDD?
So okay. So that's a good point. It's definitely faster. Now, it's variable latency depending on what sequence of operations do you have to do. Let me restart. It might be variable latency depending on what sequence of operations do you have to do. So let's say you have to write completely new piece of information, right? This has never been written before. You find a page that this information has to be written to, and you write it there, right? And this also assumes that you have a page available that has already been previously erased. Right? So all of these things have to fall into line for you to be able to write relatively quickly. And I don't know exactly what those numbers are, but probably of the order of, let's say, 20, 30 microseconds, something of that sort. Right? Now, let's say you want to write a new piece of information, completely new piece of information, but you have no erased pages available to you. Now you have to go and find a block or a page that you have to first erase, right? And then make it available for writing this new piece of information. And that sort of introduces this sequentiality of steps. So you first find a page that can potentially be erased, and then you write this new piece of information into it, and that takes longer, right? So even though the same amount of information is supposed to be written, the state which your SSD is in determines how much latency this particular write is going to take. And then let's, for the sake of completeness, let's assume that it's 4 kilobytes, right? So each and every case. So the first case was the fastest. The second case is a little slower than that. Now let's say what I want to do is I have an already written 4 kilobyte piece of information somewhere sitting on my SSD, and I need to modify it somewhere else. Or I need to modify some portions of it and write it again. What I need to do in this case is I want to read out that piece of information that's already on my SSD, modify whatever I need to modify, and then write it back, right? So now first there is a read, there's a modify, and then there's a write, and then the write could either be one of those two steps that I had talked about before, right? So this could potentially be a very costly operation if it was the second write from previously. Right? So again, depending on what it is that you want to do and what the state of your SSD is in, it might be costly, or there might be variable latency for your write, but it's possibly never going to be as costly as writing to a spinning wheel. I hope that makes sense.
Yes, sir. It makes sense. Thank you.